Hey, everybody, this is Larry. This is day 29 of the March Leetcode Daily Challenge. Only 3 days left. I hope y'all are doing all right. Today's problem is find a duplicate number. It's a medium 287, and let's get started. Hope everyone's having a good week and having a good rest of the week. Let's finish this month strong, get that streak going, get those problems solved, and let's go. All right, given an array integers nums contain. Oops, the hell? Containing n plus 1 integers where each integer is 1 to n. Okay, so isn't there? Okay, so basically one number is repeated and then we have to remove it. We cannot modify and only use constant extra space. I don't like these forms because the tricky thing is about the constant extra space, but it's just so particular that it's not really that engineering-y. And also I think this one I feel maybe it's okay. I feel like this is also one of those problems where if you haven't seen it before, it's definitely give it a go. It is kind of interesting and fun in a brain teaser kind of way, but not super. I don't know. It just doesn't like the skill is not crossover. But that said, maybe that is the case with a lot of competitive programming. So maybe that's a fair point. But the constant extra space is just a little bit weird. So I don't know. So I think this is fine. The key thing to notice for this one is that if you have given the sum of this array from 1 to n, the sum from 1 to n is going to be something like, let me write it out. And actually, I'm not going to lie, I actually don't remember this one. Or at least, I remember this one, but I don't remember if this is this or -1, right? And the way that I always have to think about it is just do the math for a small number. I know that, for example, 1 plus dot plus or just plus 4 even, right? So this is n equals to 4. I also know that this is equal to 10, for example. So I'm not gonna lie, I just do 4 times 5 over 2 is equal to 10. So that I know that is the plus 1 and not the -1. I'm not gonna lie, I mess it up all the time. It's just not, I don't know, it's not worth remembering. But now that I know is this one, that I know that the sum of the numbers, so I've total is equal to this, and I also know that if I calculate it, so okay, let's say m is equal to length of this nums array, then n is equal to m minus 1, and then the projected is equal to total minus n times n plus 1 over 2, right? And you could prove to yourself that this is always an integer, by the way, in case you're curious, just by pigeonhole maybe. But yeah, so then now you have this number. The total is the sum of all the numbers here, knowing that one number is repeated once, or repeated once or repeated twice. What's the vocabulary? Anyway, one number is repeated, right? And then you have the total, which is this thing, and the actual number. So yeah. This should be okay as long as I just want to double check that. I don't know. I mean, I think this is okay, but I just want to make sure my inputs are right. All right, let's give it a submit then. How did I get it wrong last time? I hope I don't get it wrong this time. Oh no. Oh, did I misread this problem again? I feel like I misread this problem 3 different times every time, so okay. Let's see. Oh, huh. I mean, clearly I make the same mistake 3 different times. I don't know how I keep doing this. I even tried it. I don't know why they don't give it. Okay, maybe that's just supposed to be a gotcha. Numbers of length is equal to n plus 1. Okay. Huh. I really just misread this, and clearly I misread this 3 different times. Okay. Whoops. But that said, if you have given that problem where you have n numbers 1 to n inclusively and only one repeated number, This would be the way to solve it. Okay. If, however, whoops, if you're giving that more than once, let's put this in here. Obviously, this doesn't make sense if, so this implication, the idea that I had was that n is equal to the number of elements minus 1. Huh. But now that I read it, I guess that's not the case, even though yeah. Oh man, I'm a little bit out of it now. I feel like I got thrown into a twist and try to think about it. Okay, so yeah, so in this case, n is obviously not equals to m minus 1. So how do we do this, right? Oh man, yikes. Let's see. Let me give it a second of thinking about it. All right. That said, apparently I've already done it twice, so you could probably watch the other video for the other explanation. So yeah, that would have been linear time, constant space, only one repeated number. What about the other thing, right? What about the other way of? Okay, so in this case, do we need to know n? Am I really misunderstanding this? How is this valid input? I'm looking at, okay, nums of length is equal to n plus 1. All the integers appear. I mean, okay. I mean, I know that it doesn't say that each number has to appear once from 1 to n. I know that, I get it. But I mean, one thing I'm trying to figure out right now, to be honest, for me personally, is just try to figure out how to, like, how can I, well, for example, how do I stop misreading this? Because apparently I misread this 3 different times. But this feels like that's how, okay. Because I guess technically this is true. Okay, let's see. I mean, the way that you would do this in this case now is just do the, I was going to say the swap scenario. So there is another way to solve the way that we have it now, or the other way is just the swap scenario. The swap, of course, is, but it's not the answer because you end up modifying the nums away, and also is a solution that I don't like anyway. But in that case, you would swap. You basically try to sort it into 1, 2, 3, 4, 5 ... n, right? So you would have something like, let's say you have this case. Now I'm giving like all sorts of chance. You would try to swap. For example, you move that into slot 3. So 1, 2, 3, and here you know that this is already duped because slot 3 is already the same number. But let's say you have another one. Let's say you have this, you would swap 1 with 1, so that's good. 3, you would swap with 4, so then you have 4, 3, and then now you swap this 4 with, I guess technically 1 of the 2, so then you have this, and then when you get to the last 2, you go, oh, okay, 2 is already used, so then now you have a duplicate number. Yeah, do we have to return the number? Okay. Here, so that's one way of doing it, but of course that modifies the input array nums. So that's not the way to do it. But now I'm a little bit confused. But how do I do it? It took like a considerable time. Okay, let me think for a second. How would I do this without modifying and using constant extra space? Maybe I don't know this one. It's just so awkwardly phrased. now I'm trying to think, can we take advantage of the fact that we know this information? Because now, obviously, what we said earlier was not true, but that means that, of course, how can we prove at least one duplicate number exists because it's a pigeonhole, right? Okay. Oh, wait, are we not supposed to solve this in linear time? That's basically what I was. I mean, can you do this in not linear time? Was that the? Hmm. I mean, you could do this in n log n time, right? In a very easy way. Um, you basically just do binary search, right? Binary search on um, counting the number of numbers that's greater than or equal to this number or something like that, and that would be very linear, very n log n just from binary search. Every time you go through the array, and then you just take the half that has the more numbers, or yeah, you take the half that has more numbers, and you know that by definition your duplicate number has to be inside, right? And that would be n log n. How do I solve this in linear time though? Hmm. Also, if you're practicing binary search, and maybe that's the intent, because I guess now that I think about it, binary search is the theme of the week. That is a technique that comes up from time to time, so definitely recommend that one. But how do we do it in linear time? Can we do some sort of like median finding or something like that? Um, um, hmm. I mean, the binary search one is a decent answer, but now that I see the follow up, I'm trying to think: is there linear time complexity, or is it something like really silly? Uh, or also whether the linear time is also constant extra space, because I guess the way they phrase it is not clear to me. Like you can do this in linear time and linear space. Um, hmm. The way they phrase it is not super clear that it is um, linear time and constant space. Um, hmm. Let me see. Let me think about it for a second. Uh, is there any other way? Well, I mean, of course, in linear time, you can also do linear space. Um, very obviously with just like a loop and a hash table. Obviously, that's the case. Um, but you can also do it with extra space, but modifying the array is what I meant with the permutation thing. But then the question is, can I do this with linear time, not modifying the array, and only using constant extra space? Hmm. Let me think about this. Hmm. I guess the way you could do it is by using Floyd's cycle detection. I forgot about that one. Um, yeah, I think I always forget about this one. But the idea is kind of the same as the permutation thing. But that's kind of a way. I'm just so right now I know that this is correct. I'm just trying to think about how to explain it to Yao at home. Um, because permutation cycle things are kind of, to be honest, I find that like I mean I understand it and I get it, but I also like it's not very it's not very fundamental, right? Or rather like it's something that you would have to learn, and it's not something that I'm trying to think about how what is the best way to explain it. um all right, let me play around this. Let me play around the explanation, I guess is what I'm trying to say. So 3 goes to 4 goes to 2, so then this is a cycle. Okay, so that's good. Then how do you get the 2 is the duplicate from that? So now this is a 3 cycle, this is a 1 cycle. The 2 does not go back to itself. So that means that this is how do I do this in good time though? Sorry, people are messaging me. I'm responding very quickly. But I mean, I remember the technique, but I don't remember how to explain it or how to code it. Um, Basically, it's the same idea of finding cycle of a linked list, but you have a function instead. The way that I usually do that one though, well, I mean, I know how to do it, but how, where you enter the cycle, and then okay, I guess that's fair. Because basically, what happened? Okay, I think I just don't remember the proofs, and that's what I'm doing in my head. But give me a second. Okay, so let me go over the solutions real quick, and then I'll explain the one that I've been kind of thinking about. So there's binary search, right? So basically, see if x I mean, you could count how many numbers there are that is x or larger. Take the half that has greater than half the numbers, right? So you take the bigger half usually. So this is going to be O of n log n time, because we have log n iterations, O of n each by going through the array. And of course, this is going to be O of 1 space, because it's just binary search. And then you have the what I call the permutation cycle, swap cycle, maybe swap cycle solution. This is O of n time O of 1 extra space, but modifies nums in place. Depends if that's okay for you. So this is going to be, how do I say it? So the way that this works is just basically swaps num sub I with the num sub I until we see a repeat. It's just pigeonhole things. Maybe you can make that argument. And then the way that we're doing it is basically building off the swap cycle solution, but without the swapping, is going to be Floyd's cycle detection or Floyd's algorithm, something like that. Or another name is more commonly, maybe not more commonly, but it's called tortoise and the hare. Basically, think of the linked list solution, right? And then now this is where I'm going to explain this part real quick. Let me plug in my drawing board. Oops. And also let me start drawing. Okay, there we go. This is plugged in. All right. Give me a second to set this up. This is also like kind of a ridiculous solution, by the way. I don't know if I mean it's either like almost brain teaser-y, like either you know it or you don't. I feel like this is very hard to get. So yeah, just to kind of give you some context. Let me see. Okay, so then the idea is okay. So let's say you have. Let's actually use. I was trying to think one of these examples, but let's say you have. Let's say you have. I don't know. I don't know, 4, 2, 3, 2, 5, 7, 6. I don't know. This is kind of terrible, but then the idea is that kind of similar to the swap thingy. So the idea behind the swap cycle is like the pigeonhole, right? If you get each you always have at least one place where that condition cannot hold. So then the idea behind this permutation cycle is the same thing. So that here, if you're just following, so let's say we have some num sub I. Let me check real quick that this is on screen, because I've done times before where I messed up. So here, if you follow this to num sub, how did this happen? Did I draw it kind of weirdly? Let's say I do something like this, right? This is terrible handwriting. Right? What does this mean? Well, that means that 1, for example, it goes to itself, so then it's happy. 4, we go to index 4, and this is 1 indexed, for example. Go to 3, go to 2, and then you see this 3 cycle, right? 2, well, obviously, this is going to go to here, so this is not in a cycle in its own. 5, 6, 7 has the same idea. I guess this is too similar. But yeah, so what happens, and there are other degenerate cases with respect to, obviously, the one that I failed the cases for, which is 2, 2, 2, 2, 2, 2, 2, dot, dot, dot. So then, in this case, you just have right? Also note that in this case, if you, I think, and this is what I was thinking about, if you go through all these cases, the thing is that there does not exist. Wait, let me see. Yeah, all the integers exist only once except for one number. So that means that if you look at these kind of DAGs, if you will, there will well, it's not DAG because there's a cycle, but if you look at this directed graph, there's only one case where the numbers do not belong in a cycle, and that cycle will have only one will only have one tail going out. For example, in this case, right, there'll only be one thing, and look at here, and so forth, right? And the reason is because in order to have a linked list, if you will, that goes outside of that and have 2 distances away outside the cycle, that means that you need another number that's pointing at here, right? Is that true? I guess actually the way that I'm saying it is actually really not true because you can easily have, what is this? 1, 2, 3, 4, 5. Actually, I messed up here. Huh. I drew the diagram very weird here. Sorry, friends. Hang on. Cannot erase. Okay, let me use the mouse to erase. Like maybe I just don't know how to do it. Sorry, friends. Oops. I drew this wrong. Okay, so here, actually, I lied then, because I can't count. All right, what I meant to say is that this is pointing at 5. 6 is pointing at 6. Nope, that's not 6. This is pointing at 6, and 1, 2, 3, 4, 5, 6. Okay, I just miscounted. So this one actually is a self cycle, right? So here you can see that there are definitely linked lists with multiple tails, but the entry point is the important part, right? That means that the entry of the cycle is going to be the one with the duplicate numbers because by definition, this number that is the entry into the cycle has two has two entry points, right? Because yeah, it has a duplicate number. I think one thing I'm trying to think about, which I maybe messed up, is trying to think about how is this linear time. I think you can do some without marking things as like used or whatever. Because the idea, the reason why 2 in this case is a good example is because, the 2 is the answer, is because there are two numbers pointing into it. Oh, actually, this is wrong, isn't it? Wow, I'm just like drawing really bad things today. Sorry, friends. Give me a second. Let me erase more stuff. This is wrong because this 2 is not pointing in there. What we want is actually this 2 is pointing into here. And then now with the first node, this node we know that has two numbers pointing to it because it has this 2 and this 2 pointing at this 4, right? And so looking at, you find the entry point, then you know that the first node that points into it is a duplicate number, and it could be either one. It could be this one or this one is a duplicate number because by definition, the two numbers pointing into it, and therefore 2 is the answer, and that's what you will return. Wow, I really this one's a little bit confusing, isn't it? Because even though I know the solution, I've been saying it wrong. So it's a good thing I'm drawing it out for you at home. But yeah, and I got confused in here because in this case, the answer was also 2. But let's say, for example, if maybe if I did it this way, it'll be more clear, right? If this number was a 3, this may have 2 cycle, but the answer is clearly 2 that is duplicate, right? Okay, so sometimes you have to use better examples and also ones that you don't get confused. But then now I guess the question is, let's say I have all this, right? Let's say I'm convinced myself it's good, it's Gucci. Then in that case, how do we get this in linear time? Because the tricky part about getting this in linear time is that we don't want to duplicate ourselves, right? Yeah, because if you do, so the reason why I'm thinking right now is if you naively, for example, if you want to, you have this algorithm that I told you, you naively go, okay, let's start at 1. Okay, that's good. Here, we're looking at the top. Let's start at 4. Okay, so that's good. We do a cycle, and there is a cycle, so that's good. But then now, if you try to do, let me change the color really quickly. Let's say you're now here. You want to know that you don't want to do this work because if you did, because if you did, then this is duplicate work, right? That means that you loop it over again. And of course, if you keep doing that, that's going to be messed up. I wonder if there's a way that we can check this. Huh, I didn't think this through, not gonna lie. How do I do this then? Let's see. Oops. Keep on knocking my thing. Wow, this one is kind of tricky, isn't it? I think usually in the past I've always done it with thing, but am I thinking about it weird? Okay, I think I have an idea. I think the tricky part, I was trying to think, right? So I think the part I was trying to think is that if we do it naively, we go, okay, we go back, we go from left to right. If we go from left to right and then just do it like naively, like, hey, there's a cycle start here, right? And so forth. I think so that was going to be n squared time if you do it naively, like I said. But I think one thing that you can do, and actually I don't need this anymore. Let me put it just away for real quickly. I think the one thing that you can notice is that let's see. Can you see this? Okay, yeah. So let's say you have the example that I have here, which is 1, 4, 2, 3, 2, 5, 7, 6, right? So this is the number that I kind of drew randomly. So then the idea here is that, well, let's just use the last number. That's basically the idea. And why can we start at the last number, right? Well, the last number is guaranteed to be not between 1 and n. So that means that this number will always lead to a cycle. And then now, but this number is leading to a cycle, but also not in the cycle, right? Because we know that in this case, the last number, no number points to it, right? So then now, hopefully that makes sense. I'm trying to like explain it live and explain it and solving this live. This is actually more interesting than I gave it credit for. Yeah, so basically, and I think in the past I probably solved it the binary search way because I don't have any recollection of solving this. Otherwise, I would have gotten it much quicker probably. But the idea is that okay, so we know that given what we said before, there are no edges, if you will, a directed edge pointing in the last number. So that means that this will always point to a cycle. And then now we can figure out which one it points to, right? So okay, so let's get started. I think that's good enough to get started because basically 6 in this case, we can even do one example, which is this one. So then here, the fast pointer and the slow pointer, so let's write fs, and then now 6 points to 1, 2, 3, 4, 5, 6. So then now fast goes to slow goes to here, and then fast goes to the 5. So then fast is at the 2, right? So that's after one iteration, and then after the second iteration, f already goes to the 2, and then 4, so it goes to 3, and then 5 will go to the 2, and then now the 3 goes to the 2, and then 2 goes to the 4, and then now 2 goes to the 4, right? And then it was at here that they meet together, meaning that there are 2 places that are pointing to it. So we know that this is good, and then now you just have to find a pointer that has and then now we know that 2 numbers point at index 2, which means 2 is the duplicated one, because that is, which indexes are pointing to 2 because by definition, like you're given that function. So okay, so I think that's what I needed to get started. Okay, so let's say slow is equal. Okay, let's say n is length of nums. Slow is equal to n minus 1. Fast is equal to n minus 1 as well. We'll start the n, and then now we go while slow is not equal to fast. Well, that's not true. So we need okay, so then maybe we do one ahead. Yeah. Is that the slow one? Nope. The fast one is the one that. Well, maybe I hope that this is right. Yeah. So then, while this is true, then slow we move forward 1, and then the fast we move forward twice, right? Oops. Okay, so then now when they meet at the answer, and I think that's it, right? Maybe, I hope this is right, because they meet at the index in which multiple numbers are pointing, and that would be the that's how you get to the index, right? It's right for the year. Let's give it a quick submit, and then we can maybe go over the other one cases. Did I mess this up? I guess so. Yikes. But today we're learning. Well, I'm learning anyway. Hope you're learning from that one. Why did I get 1 on this one? I feel like it's because like I messed up a little bit on the off by ones. I think this was what I was a sketch about, like whether I should start here or move 1 more from here. I think that may be the thing. But let's see. Now we have a case to kind of go out and play with it. Yeah, so 2 points at this one. So then slow is equal to did I mess up? I think maybe I messed up, that's why. Because this is the last number. I think it's just because of this loop. I actually don't or maybe the other one. I mean, I think they should start at the same spot, but then this loop is a little bit weird. What I want is kind of like a do-while loop. Let's just do first or this. Something like that, maybe. I actually wanted a do-while loop, and I kind of hacked around the do-while loop, and now it's giving me wrong answer. Well, this is still wrong though, so basically you look at the, okay, why is this wrong? Is this right for the last number? Okay, so now we have a easy example of 1, 1, 2. First we start at 2, they both, so this goes in, 2 goes to 1, goes to 1. Wait, what? So they're equal. I'm just being dumb. The reason why I'm messing up is because I'm using 0 indexed. Yeah. And then like it was, I'm actually kind of, sometimes it's kind of weird in that you have good luck in that it passed all the example cases, you know? And then now I have to add 1 because now it's the, because I was getting the, I was getting right answer for a lot of those cases, as you saw. Like that's why I have a false sense of confidence. But I put in like 5 test cases and I got them all right by accident. So okay, let's maybe now give it a submit. Now that we added this extra case, hopefully this is right. If not, that's a little bit silly. Okay, fine. I'm still a little silly. So maybe I need to work that out. Okay. Put it 2. Did I mess it up? Why did I put 2? Do I need the number that's in that index? No, that doesn't make sense because here we would meet at 4 unless I messed up something. And then the number pointing to it is 2, right? Oops. And that is not the numbers in the 4th index, it's just the index, which is 2. So why is this wrong? Okay, so let's say we start at 4. 1, 2, 3, 4. Now 4 points to 1, and okay, let's look at this together. So this is, so in the beginning this is 4 and 4, and then now the slow one goes to 1, and the fast one goes to the index 2. Okay. Right? Yeah, because it goes to 1 and then 1 goes to 2. And then now the slow one goes to 2, and then the fast one also goes to 2. And then I return 2 as the answer. Or the number, the index 2. Did I think I messed it up then, because now, oh wait, maybe not. I think I made a wrong assumption. So what I was assuming, no, I think not. I think I just have an off by 1, and that's why this is wrong. And why I say that is because I had an off by 1, so then now it's not matching where, because if you look at the graph, don't want to draw it, but basically having this, I just have an off by 1. If you look at this graph, 4 points at here, 1 points to here, and all these numbers, like you have multiple numbers point to 2. So then we should meet at 2, the number, or the first index, right? So that should be the answer, but I'm having an off by 1, so it moved 1 extra step, which is why I was worried about this particular part. I think this is right then. But I just had issue with an off by 1 the other way, maybe. Let's see. Still wrong though. Is this the right answer or right index? Yeah, maybe I did it. This one is the wrong one. Huh. Wow, yikes. Alright fam, this is clearly one of my longest video in a while. And I have really wrong answers. And this is also where off by 1 is giving me a lot of issues. Well, now that I fixed this one, but now I don't fix the 4. Or I don't fix the example case. Expected end is 2. So 2. So the entry point is correct in that it should. But why is this wrong? Let's just actually print more stuff. Print slow, fast. So okay, so it starts point after one. It's both started at 2. I hope that's right. Yeah. And then after one iteration, it goes to and then meets at 3. Oh, I see. Wait, do I? So it meets. I think I just messed up. Also, like, how do I keep on getting the right answer for my test cases? And then just, because this isn't even close. Okay, so I think now we see that we're at. Okay, so then now slow is equal to fast after we move to index 3. Or the last value of it is 3. Okay, I think we're okay. So I think I just had another off by 1 situation where it thinks the answer is the value is 3 but not the index because I already moved. So okay, so maybe I just need something like basically the one that's before it moved, and something like that maybe. Give it a spin. Huh. Oh, I guess I should print it just to. Yeah, so this is 2. Man, I'm really messed up right now. So the slow. Okay, so let me just actually work through a case. Okay, so that's it here. The fast move 2 steps, so it goes to index 2, 3. Oh, maybe I have an off by 1 because why would it go to 1? Okay, so it went from outside, it goes to 2 is the slow one. Okay, and then okay, where do you get the 1 from though? Did I mess up with the -1? Maybe I did. Because 2, we want to go to 1. Okay, that's fine. Okay, no. So it goes from 2 to 1, 1 and 2. Okay. And then now it goes to 2 and 1 because 1 goes to itself. Yeah, 1. No. I'm confusing myself. Sorry, friends. How do I get a 1 then? I'm doing something really wrong, clearly. So give me a second. I mean, the idea is right, but my implementation has just been really terrible the last week or so. So yeah, 2. This 2 goes to here. So the fast pointer is at the 3 and the slow pointer is at the 2. So after one iteration, this should be 2 and 3. But that's obviously not the case. Right? So why is this? Am I missing something weird? Let's see. Because it should start at 4. So then it takes this, it goes to index 1, and then it goes to index 2, which is No, I mean, either way. Oh, these are the pointers. Pointers are always confusing, even if you have a lot of experience. So, okay. So that means that after one iteration, slow is here. So then now it is the okay, I think this is right. Because instead of the value of the pointer pointing at here. Okay. So that means that after one case, so this is a little bit off then because we shouldn't have no, you have a pointer pointing at 2, but it is the value of here. So we have a pointer pointing at 3, at 4. Is that right? Oh no, that's the fast pointer. So that's right. Okay. Okay. Let me. This is where, to be honest, I if I wasn't lazy, I would have done this a long time ago. On my on like a piece of paper and notebook. If I was having a problem with this contest, like if I was having a contest, I would have start drawing a long time ago. Because sometimes, especially with pointers, it's very easy to get a little bit lost. So let me bring up my drawing board again, even though I said we don't need it, because I am just confused about debugging and I am bad at it. So let's see. So now we have let me change the color back to a darker color. What's it? 1, 3, 4, 2, 2. So we start by having pointers pointing at the last element, right? And then after one iteration, the fast pointer will now point to, let's just say this is fast and slow. They point at the 2. So then after one iteration, the fast would go to 3 and then 4. So then now this is the new fast and this is the new slow. But keeping in mind that this is the pointer. So F is actually here. I think that's the confusion I have, pointing here, while S is here, pointing here, right? And then because of that difference, by the time they match, I think that's why we have an off by 1 and I'm mucking it up regardless. So then this is the first iteration. And after this, and then now we do a second iteration. Now fast goes to 4. So go to 4, so it points to here, and then goes to 2. So then now fast is here, pointing here. And the slow is here, pointing here. Okay? And then now we do another iteration. Slow is now pointing here, and fast is now pointing here. Right? So that means that now they both point at this thing. They make up here, which is already wrong, I think. That means we have an off by 1 somewhere because they're not. Oh wait, am I messing myself up? I think the algorithm is not supposed to. I think I'm just forgetting about the algorithm. The algorithm is not supposed to meet up at exactly the beginning of the point, right? I just mixed myself up. It's supposed to meet somewhere inside the loop, and now that we have a loop, we can now calculate it by. We can now calculate the looping thing by having the entry point of the loop by just sending the fast pointer out again, right? I think I just forgot about the Floyd algorithm. It's been a while. Hi friends, that was a mess. That's why this doesn't work. I just forgot a whole piece of the code. Okay. So then now, and actually, yeah, right. I'm just double checking this code. And then now we have a pointer that's inside the loop, and we just want to put set fast is equal to n-1, and then while slow is not equal to fast, oops, we do this thing again. That's why. We don't need this. I think I confused myself a lot. It's either this or the pointer pointing to it, so I might have to take a look into it. This was a big yikes. I'm really bad today, or just like recently. Okay. That add one. Well, that's still the wrong answer even if I add one, but. It's either this or maybe the number pointing to it. No, that's not even right. So entry point is 3, so that's good. I'm just now checking whether this is, so this is giving me the index in which they're matching, I think. Yeah. So then I'm just, okay. So I just do this rather. No, because they're both matching, so that's not right. You want the number before this. No, I think this is, am I confusing myself some more? Sorry friends, this is a very slow one. It's very easy to have off by ones on this one. Is either that or I'm, oh whoops, this this is not supposed to be fast. Oh, not twice. Okay. Okay, I think now we're good. That's what happens when you copy and paste. But basically, I mean, I'm not gonna go over that much here. But if you do want to know more about Floyd's algorithm, do find cycle in a linked list. I think I have a good explanation in that video, so definitely check that out as to why this works, and why they match at the or they meet at the entry of the loop. Let's give it a submit. Hopefully this is okay. Cool. 728-day streak, and this is very tough and earned. I probably just did the binary search answers before. I'm curious whether. Okay, binary search. Also binary search. Okay, so yeah, so it's kind of cool that I did it a different way in learning. But I have the idea and it's right. But I think I had it too much of a as a black box that I forgot the details. But also that said, Floyd's cycle detection is not something that comes up that often. So I don't know. Maybe that's an excuse. But this is basically Floyd's detection. You find the entry point and then you return the pointer to that entry point, which is by definition is slow. I definitely spent way long here. My implementation has just been really bad the last couple of weeks. Maybe I need to do more practice or something weird. But yeah, this is going to be linear time and constant space because we only have pointers. Yeah, I think that's all I have. Let me know what you think. I know this is a long video. Hopefully you watched it okay, or did it in fast forward, or did something, I don't know. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. Did you do it this way? Did you do it another way? I don't know. I'll see you soon. Stay good, stay healthy, to good mental health. I'll see you later. Bye-bye.